Hello, students. Can you hear me? Can you
Yes,
hear
ma'am.
me, students? Okay, thank you. Right. Um, Good afternoon, all of you. Yesterday we started our second chapter, basic concepts of probability. So in this chapter, you will learn how to do an experiment and how to list possible outcomes for an experiment, and then how to assign probabilities for events and outcomes. Okay, and then you will learn about conditional probability as well. Okay. Let's see what we did yesterday. We defined uh, about experiment and random experiment. Then we discussed some examples for experiments. Then we learned about sample space, sample point, then events, uh, and a graphical representation of sample space and events. Yes. So let's start with probability today. If you can remember, I taught you how to find a probability for an outcome or for events, right? Okay. We did this example as well. I think we last time we were discussing about types of events, right? So we discussed these main four types of events, that is certain event, likely event, unlikely event, and impossible event. What do you mean by certain event? I hope you can see my screen. Okay. Certain event is the event is definitely going to happen. If you want to find the probability of a certain event, that probability is definitely 1. That means we are 100% sure about uh, these events, certain events. Okay. So likely event is the event will probably happen, but not definitely. So you have an example given here, probability of getting head if coin is tossed. We may get either head or tail. Okay, so it is a likely event. Okay, there's another event as unlikely event. Unlikely event will probably not happen, but it might. Sometimes it might happen, but probably not. Then impossible events. What do you mean by impossible events? Or we say uncertain events. Uncertain events. That means the probability of that event is going to be 0. The probability is none. Okay, that event is never going to happen. Okay, there are 4 types of events: likely event, unlikely event, impossible event, and certain event. Let's learn another event, simple event. Simple event means an event corresponds to a single possible outcome of the experiment. For example, if we roll a fair die, we can get the sample space like this: 1, 2, 3, 4, 5, 6, because the die has 6 sides, no, numbered from 1 to 6. So if we define an event as getting 5 on the uppermost face, okay, if we define an event like that, how many elements are there in that event? How many elements are there? Getting 5. Now the event is defined as getting number 5 on the uppermost face of the die. So in that event, there's only one element, that is 5. So if it has only one element, we call it as a simple event. Simple event. Clear? Right. Then let's discuss about complement. What do you mean by complement? Here, the complement of an event A. So that means we have an event A. We are going to learn about the complement of A. The complement of an event A with respect to capital S. Now, what do you mean by capital S? S for sample space, right? Sample space means what? It includes all possible outcomes of an experiment. Okay. The complement of an event A with respect to the sample space is the subset of all elements of S that are not in A and is denoted by A dash or A complement. Did you understand it? That means the complement of A means a subset of all elements of S that are not in A. Here I have given you the graphical representation of complement. For example, here we have the sample space, capital S. Okay, there are two events, A and B. Right? The first circle is for A and the second circle is for event B. If we want to find A dash or A complement, that means all the elements of the sample space, that are not in A. That means the sample space except the event A dash. You can see that A dash in red color in this region, in this Venn diagram. Understand? So A dash is what? Complement of A. All the elements of the sample space that are not in A dash. Okay, clear? Now intersection. What do you mean by intersection? If we have two events like A and B, okay, sometimes there may be an intersection region, for both events A and B. We denote it as A intersection B. We use this symbol to denote intersection, right? Intersection. A intersection B is the event containing all the elements that are common to A and B. Intersection means the elements that are common to A and B. You can see that region in this Venn diagram, intersection. A intersection B. Understand? Let's do some examples to understand this intersection and complement, okay, later. Right. Now, mutually exclusive events. Now you are doing probability now. So you have to be familiar with these statistical terms or probability terms. Okay, that's why I'm teaching these things. Mutually exclusive events. What do you mean by mutually exclusive events? Here, it's given as two events are mutually exclusive or disjoint if A intersection B is a null set. That means for, let's say we have two events A and B. If we can find an intersection region, or if we can find a region with common area, common region for both A and B, that means those two events are not mutually exclusive. They are not mutually exclusive if it has a common region. But here, here mentions if A intersection B is a null set, then those two events are called mutually exclusive events. You can see that in this diagram. Here we have two events, event A and event B, and you can see that there's no any common region, common elements. Therefore, A and B are called mutually exclusive events. Mutually exclusive event. The requirement is A intersection B should be a null set. It doesn't have any element. If we consider the set A intersection B, it does not have any element if they are mutually exclusive, A and B. Is that clear, guys? I hope you understood about mutually exclusive events and intersection and complement. Okay, then we will discuss about union. The union of two events A and B denoted by the symbol A union B is the event containing all the elements that belong to A or B or both. That means a union B means all the elements belonging to A, B or A or B. Right? That you can see that A union B in this diagram, the red color region, that region represents A union B. The elements that are belonging to both A and B, both A or B or A or B. Okay? All three regions, these three regions need to be considered for A union B. Okay? Now we discussed A intersection B, A union B, A complement or A dash, right? Okay. Now we will do this example, exercise 1. Here you have two events or two sets, right? A is 1, 2, 3, 4, 5. These are the elements of set A, 1, 2, 3, 4, 5. And again we have another set or another event called B. The elements of event B are 2, 4, 6. Okay. Now we want to find A intersection B and A union B. Now what you need to understand here is A intersection B is another event. It is another event or another set. Okay. So what is A intersection B? A intersection B? A intersection B means what? Elements that are common for both A and B. What are the common elements? If we consider 2, set B has number 2 and set A or event A also has number 2. Right? Now 2 is a common element. Another one, tell me. Yes, 4. 4 is again common for both. Is 6 common? No. Only 2 and 4 are common elements. Therefore, we can write A intersection B as 2, 4. Here also we use curly brackets because A intersection B is again an event. Okay. Therefore, we have to put these elements 2 and 4 in a curly bracket. Understand? Okay. Now, let's find A union B. A union B means what? Union B. All the elements belongs to A, B or both. So what are the elements? All the elements belongs to A or B or both. What are the elements? 1, 2, 3, 4, 5. Now 2 is we have written it earlier, no? 2. Therefore, we do not write number 2 again as we have written it once. Then 1, 2, 3, 4, 5. 4 has been written earlier. What is the next one? 6. 1, 2, 3, 4, 5, 6. We do not write 4 and 2 again, right? That's wrong. We are writing common, not common. We are writing all the elements now. So we usually do not repeat elements when we write union, A union B. Understand how to write these A intersection and A union B? Did you understand, students? Yes or no? If you don't understand, please let me know. That is very easy to understand. Therefore, let's move to the next section, events based on Venn diagrams. As I mentioned earlier, we can represent events using Venn diagrams as well. Okay, so we discussed earlier about complement of an event, then A union B, A intersection B, or mutually exclusive events we discussed. No, now we are going to represent those events using Venn diagrams, or we are going to identify regions with that means discussed events like A complement, B complement, A union B, A intersection B. Likewise, we discussed some events. Now we are going to identify those events in this Venn diagram. Clear? Right. Here we have used a Venn diagram with two events, event A and event B. And universal set is given, is not denoted by capital S or sample space. Okay, capital S here, the event A and event B. If you can see this region, this red color region, that is A intersection B. A intersection B is represented by this red color region. The elements that are common for both A and B. Usually when we read it, A intersection B, or we can read it as A and B. A and B. For example, if you are asked a question like find A and B, A or B for above Venn diagram. Suppose you have this question. So what do you mean by this A and B? A and B means A intersection B. A intersection B is called A and B. A or B means O. We have term O, which means A union B. Understand? A union B. Therefore, okay, before coming to the De Morgan's law, let's discuss these things more. Now we have two events. We have identified the region A intersection B, or A and B. Okay, now tell me about this region. What is that region? What is the, I mean, here we have the graphical representation now. Can we represent the same region using symbols? Using symbols. That is what? A intersection B dash. A intersection B dash. That means elements belongs to A and B dash. What do you mean by B dash? Complement of B. That means B dash is this region, B dash. And that region must be intersected with A. Therefore, sorry. Therefore, give me a second, students. I hope you can see my screen now. Right. Sorry for the inconvenience caused. Anyway, we were discussing about events based on Venn diagrams. No? So we discussed how to identify A intersection B or A and B. Then we discussed A and B dash. A and B dash. That means the elements common for both A and B dash. Right? Then how can we identify this region? Surely it should be A complement or A dash, and A dash must be intersected with B. Therefore, we can represent it as A dash intersected with B. So A dash and B. Okay, try to identify these regions when you have Venn diagrams also. Okay, it's really important in probability identifying these regions when you have Venn diagrams, right? So if you have any questions, any problem regarding these regions or regarding these Venn diagrams, please ask me. Okay, now we are going to learn about two formulae used in probability, defined as De Morgan's law. De Morgan's law, because these two formulae have been found by De Morgan scientist. The first one is, there are only two equations, two formulae, right? The first one is A intersection B halting complement is equal to A complement union B complement. There's a pattern, there's a relationship. You have to identify it. So we have A and B dash. A and B dash, or A intersection B halting dash. So when we remove this bracket, okay, when we remove this bracket, it becomes A dash B dash, but this intersection becomes union. Understand? Now we are removing this bracket. Now we are going to take this complement into the bracket. Therefore, it becomes A dash union B dash. Clear? That is the first De Morgan's law. Let's discuss the second one as well. If we have A union B dash, previously we had A intersection B dash. Now we have A union B dash. Now we want to remove this bracket by taking this complement into the bracket. Okay. Therefore, we write A dash B dash. Earlier we had union. That union becomes intersection when we remove the bracket. Understand? Is that clear? So we have only two formulae, De Morgan's law. First one, A intersection B dash is equal to A dash union B dash. The second one, A union B dash is equal to A dash intersection B dash. Now let's see how to draw these regions in Venn diagrams. Okay, look at the diagram. Look at the diagram here. The square is used, or the rectangle is used to represent the universal set. Universal set. That's why here I have given the symbol capital U. Okay, we have only two events, A and B. Now you already know how to identify this region. That is the region A intersection B, right? Now what is A intersection B dash? That means complement. All the elements except A and B. Here the yellow color, it is given in yellow color. A intersection B dash, or A intersection B complement. Clear? Okay. So this is the left hand side of the previous formulae. Now look at the right hand side. Here we have the universal set represented by this rectangle, and we have two events, A and B. Right? Now see the region in that's not yellow, maybe light green color. That is what? That region is what? A dash, A complement. Clear? A complement. Now consider the second diagram, this one. Here we have shown B dash, or B complement. All the elements in the sample space except B, right? B dash. Here we have represented A dash and B dash. Okay. Now what's about A dash union B dash? A dash union B dash, or A dash or B dash. You have to add these two regions, no? To find A dash union B dash. Then it's going to be A dash union B dash. This region. Finally, you can compare these two regions, this one and this one. What can you conclude about these two diagrams? Finally, we have got same regions, no? Same regions. A intersection B dash and A dash union B dash are going to be same finally. Is that clear, guys? Therefore, the first law of De Morgan's is correct. We are not going to prove it, but we just check whether it is correct or not. Okay, we are not going to prove it. These have been already proved by De Morgan's. So you can use these laws or these formulae without proving. Okay, you can directly apply these formulae in problem solving, right? Okay. Let's discuss the second De Morgan's law. A union B complement, that is equal to A complement intersection B complement. Here, consider this diagram. Now see first two diagrams. Here we have A union B. It is clear. Now this is second one. That is the region A union B complement. All the elements except A union B in green color. Okay, right. Now look at these three diagrams. Second set of diagrams. First one, there we have A dash, okay, A dash. The second one, we have B dash. Now consider A dash or B dash. A dash or B dash means A dash and B dash. Finally, we will get this region as A dash and B dash. Not O, sorry, mistakenly I said O, not the term O. We have to use A dash and B dash, okay, not O, sorry for that. A dash and B dash. O means union, right? Intersection means and. So we have represented A dash here, then B dash here, and we need to find A dash and B dash. A dash and B dash is given in last diagram. Okay, A dash intersection B dash, or A dash and B dash. Finally, you can see that this one and this one are same. Okay, that means A union B dash is equal to A dash intersection B dash. That is the second law of De Morgan. Understand? So without proving this formulae, you can use these properties or these equations in problem solving. Okay. Now we are going to learn rules of probability. There are some rules we use or we use in this probability. The first one is additive rule. Okay, so first learn about additive rule. There are more additive rules, but here we are talking about additive rule for probability, right? Additive rule of probability. Okay. First one, if A and B are any two events, those two events can be any of the event, right? Then probability of A union B can be written as probability of A plus probability of B minus probability of A intersection B. You can use this rule whenever you have probability or whenever you have two events. Okay, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Actually, here we have probabilities, no, probability terms, no. We can apply the same concept for number of elements in the events as well, like this. Let's say we have two events, any two events A and B. So if we want to find A union B, the number of elements in A union B can be represented by this N. No, N means number of elements. That's going to be NA plus NB. Now, what do you mean by NA? Number of elements in the event A plus number of elements in the event B minus number of elements in A and B. This is not the additive rule of probability. This is the additive rule of probability, but we can write this as well for number of elements in these events. Okay, usually we use this rule, but if you want, you can use this N of A union B equals N of A plus N of B minus N of A and B. Is that clear? That is called additive rule of probability. Now there's an important thing here. If A and B are mutually exclusive, here it is not mentioned about these two events. It says if A and B are any two events. It can be any event, right? But here it says if A and B are mutually exclusive events. Mutually exclusive means what? You know, the intersection part is going to be a null set if they are mutually exclusive. If you can remember, if event A and event B are mutually exclusive, there are no any common elements. Therefore, this term, yes, this term is going to be 0. Okay, forget about this one. Come to the equation this. If A and B are mutually exclusive, then this A and B set is a null set. Right? It's a null set. So null set means how many elements are there in a null set? 0. Understand? Null means no. Then number of elements in a null set is 0. Therefore, what's about this probability of A and B? If there is no any element in A and B, then the probability is going to be 0. No? It's obvious. No? Therefore, it's an important rule. If A and B are defined as mutually exclusive events, then you can write this formula as probability of A union B as PA plus PB. This is true only for mutually exclusive events, okay? That's why here it mentions if A and B are any two events, then we can write this formula. But if A and B are mutually exclusive, then this formula becomes PA union B equals PA plus PB, this one. Clear? Understand, students? Because probability of A intersection B is 0. If number of elements of A intersection B is, not null, it's 0, then the probability is again 0. No? Therefore, this formula becomes this new one when they are mutually exclusive. Understand, students? So there we define that additive rule when we have two events. Sometimes we may have 3 events, more than 2 events. So if we have 3 events, any 3 events, A, B, and C, then the formula becomes probability of A union B union C is equal to PA plus PB plus PC minus probability of A intersection B minus probability of A intersection C minus probability B intersection C plus probability of A intersection B intersection C. So we can understand this formula using a Venn diagram easily, right? So let's look at this Venn diagram. Have a look. Now you have to identify these regions, okay? This circle is represented by A, okay? That is event A. Then event B, this is event C. Now you can see there's a region with red color. That region can be denoted as A intersection B intersection C. Common elements for A, B, and C. Understand? If we have 3 events, there could be elements which are common for all the events, no? Events A, B, and C. So that region can be represented by or can be denoted by A intersection B intersection C, which is given in red color. Okay. Now look at this A union, not union, A intersection B. A intersection B. That region is not actually this blue color one, but you have to understand it very carefully. A intersection B means this whole region. A intersection B. Here we have A, B, A intersection B is this, the entire region. Understand? A intersection C is this entire region. A intersection C. And then B intersection C. B intersection C. Not this region in blue color. Understand? Right. Now, if we want to find A union B union C, we need to add, if we are writing the same formula in terms of number of elements, NA plus NB plus NC minus NA intersection B. A intersection B minus, right, NA intersection C, this region, minus NB intersection C, right? Plus finally you have to add this red color region, that is NA intersection B intersection C. Here I have written the same formula in terms of N, right? But the original one was in terms of P, probability of this. So if we want, we can write this as number of elements in this set is equal to NA, NB, NC minus NA intersection B, NA intersection C, NB intersection C plus NA intersection B intersection C. So that is called additive rule. Okay. So if we write it in terms of P, then it becomes additive rule of probability. So if we have 2 events, we have a different formula. If we have 3 events, then it becomes a different one. You need to remember these 2 formulae. Okay. Right. There are more rules to be discussed here. The second one, law of complement. There's another rule that is called complement law or law of complement. That is, if the probability of an event A is denoted by PA, then PA dash can be written as 1 minus PA. Did you understand it? If the probability of an event A is denoted by PA, then PA dash is equal to 1 minus PA. Did you understand it? Okay. Give me a second, I will explain it. Let's say we have 2 events. Sometimes we may have more than 2 events, but let's say we have 2 events A and B, right? Now the probability of the event A is given as PA. It is given. It can be any number from 0 to 1. I told you probability is represented by a number from 0 to 1. No? Therefore, that probability can be either a fraction, decimal number, or percentage. Okay, I will teach you those things later. For now, remember, this PA is a number from 0 to 1. Now we want to find PA dash. PA dash or PA complement. So how can we find PA complement? This is the universal set, no? Capital U or capital S, the sample space. Can you tell me what is the probability of the universal set? The universal set. What is the probability of the universal set? There was a question in the question paper last time. That means for your seniors, 17-18 batch. There I gave, yes, I gave them a Venn diagram with probabilities. Usually we use Venn diagrams to denote number of elements, no? Number of elements, no? Number of elements in the sample space or the universal set, or number of elements in the event A, event B. Likewise, we usually use Venn diagrams to represent number of elements. But in that question paper, I gave a question with probabilities like this. Okay. This is the universal set. A, B. The probability was given here, like 0. I can't remember the values. 85, 0.1, like that. I gave probabilities. Now my question is, if we have used a Venn diagram with probabilities, then what would be the probability of the universal set? Universal set. In this case, we have used capital S no sample space. Then what is the probability of this? You should remember it. The probability of the universal set is always equal to 1. That is the total probability. I will teach you those things later, but for now you have to remember the probability of a universal set is always equal to 1. Understand? So here, event A is defined as this, and the probability of event A is given as PA. It can be any number from 0 to 1. And if you want to find PA dash, the complement of A, the probability of A complement, that is going to be what? 1 minus PA. That is a rule, law of complement. Okay, how can we find that? I told you A dash is represented by this region, A dash. The elements in the sample space except event A, right? This region. So what is the probability of that region? Probability. That region needs to be divided by the entire region. The entire region means the area of the rectangle. Or PA dash is going to be NA dash divided by NS. No, I told you. Oh, I taught you the formula we use to calculate probabilities, right? So if you want to find the probability of A, then we need to know number of elements in the event A and number of elements in the entire set or entire sample space, NS. In this case, we want to find A dash, no? Therefore, this formula becomes NA dash divided by NS. Now, how can we find number of elements in the complement of A? Complement of A? You know, A dash plus A is actually equal to the sample space, no? A dash and A. Can you understand it? Give me a second. Right? A, B. This is the universal set. Again, I lost the screen. Okay. We were discussing about the law of complement, right? So we have a Venn diagram with two events. Now try to understand this, right? A and A dash. Now my question is, what is A union A dash? A union A dash. What is A union A dash? It should be the universal set. Understand? A and not and A O A dash. A O A dash. Right? So that A union A dash represents the universal set. Therefore, number of, and again there's a question, what can you say about these two events, A and A dash? Are they mutually exclusive or not? What do you think? Are they mutually exclusive, A and A dash? If they are mutually exclusive, that means there should not be any common elements for both A and A dash. So are there any common elements in these two regions, A and A dash? There's no any common element. A and A dash are two mutually exclusive events. Therefore, if we want to find A union A dash, right? We can write it as NA plus NA dash. Understand? And we know that that is equal to this NA union A dash is equal to N universal set, number of elements in this sample space. Okay? Therefore, if we divide the entire equation by N sample space, this becomes what? N epsilon over N epsilon means 1. Okay. Here we have N A plus N A dash divided by N S O epsilon, right? Here also N epsilon. Now NA over N epsilon is what? PA. PA plus PB. We have proved it. Actually, we have discussed this rule, additive rule. Here we have A dash, right? Not B, A dash. And we told you, if we have two mutually exclusive events, A and B, then we can write PA plus PB is equal to PA union B. I told you that. Here A and A dash can be considered as exclusive events, no? Mutually exclusive events. Therefore, PA dash going to be 1 minus PA. I'm not going to give you this as a question in the question paper, but you need to remember this rule, right? So PA is, yes, PA dash can be written as 1 minus PA. Okay, PA dash is equal to 1 minus PA. Here P means probability, right? So this rule is called the complement rule or law of complement law. Did you understand it, students? Huh? Did you understand it? Complement law? Yes or no? If you don't understand, please ask me. I told you, if you can remember, if we have an event A and if you want to find the probability of A, that can be written as NA over NS. This is a rule. This is how we calculate a probability of an event. Okay. In previous case, A and A dash are mutually exclusive events. Therefore, when we write P, not PA. Yes, we can write probability of A union A dash as PA plus PA dash, since they are mutually exclusive. Right? Now PA union A dash means probability of the sample space. No? I told you probability of sample space is always equal to 1, and that is equal to PA plus PA dash. So PA dash can be written as 1 minus PA. So that is the law of complement. Okay, now we have an exercise to do. Let's do this exercise. Okay, in a group of 40 people, 10 are healthy and every person of the remaining 30 has either high blood pressure, a high level of cholesterol, or both. You need to understand a question very clearly. Okay, therefore read the question very carefully. In a group of 40 people, 10 are healthy and every person of the remaining 30 has either high blood pressure, a high level of cholesterol, or both. That means there are only 2 diseases, high blood pressure or high level of cholesterol. 10 are healthy now. Among remaining 30, okay, some people have high blood pressure and some people have high level of cholesterol, and some have both diseases, either high blood pressure or high level of cholesterol. Okay, if 15 have high blood pressure and 25 have high level of cholesterol, you have to answer some questions. Okay, first of all, you need to give this information using a Venn diagram. It's not necessary, but it's better. We can draw a Venn diagram to represent this information. Understand? Therefore, first thing is to draw a Venn diagram for this information. Clear? Okay, I will draw it here. Usually we use a rectangle to represent the universal set or the sample space. In a group of 40 people, from that phrase we can actually find the number of people in this experiment, considered in this experiment, is 40. Therefore, this, that is 40 number of people in the experiment or in the sample. Okay, or the number of elements in the sample space is 40. There are only two diseases now. So we can use circles to represent these diseases, disease A and B. Actually, we don't need to put symbol A and B because we have the disease names. The first one is high blood pressure. And the other one is high level of cholesterol. Let's say HLC. Or you can write blood pressure and cholesterol. Okay, right. It says further 15 have before that there's a sentence 10 are healthy. 10 are healthy means among these 40 people, 10 people do not have any of the disease. They are healthy. That means we need to put that 10 here. They don't have any disease. Clear? Among the rest of the group, that means 30 people has either high blood pressure or high level of cholesterol or both. If 15 have high blood pressure, it says 15 people have high blood pressure. So we have to put 15 here. They have high blood pressure, 15. Not here, right? Not here, but on the circle. 15 have high blood pressure and 25 have high level of cholesterol, 25. So we have to put 25, we have to write 25 on the circle for high level of cholesterol. Now you might think 15 plus 25 is 40 now. But it says the remaining 30 has either high blood pressure or high level of cholesterol. But here, if we add this 15 and 25, it becomes 40. That's why I told you to write these numbers on the circle, not inside the circle, but on the circle. Because this 15 represents not the people who have only high blood pressure, they have high blood pressure. Sometimes some of the people among this 15 might have high level of cholesterol as well. We do not know. That's why we are putting or we are writing that number on the circle. Clear? I know definitely you have done these things in your O levels, okay? Then 25 have high level of cholesterol. Among that 25 number, some people may have a high level of cholesterol or high level of high blood pressure or both. That's why we write that number on the circle. Understand? Now there are some questions to be answered by us. How many people have high blood pressure and a high level of cholesterol? That means there are some missing information. They are not missing, actually we can find them. These are the information we have now. Using this information, we need to find how many people have high blood pressure and high level of cholesterol. So how can we find that value, that number? To find that, we have to use a formula we discussed earlier. What is the formula that we are going to use? What is the formula that we are going to use? If we have two events, if you can remember, I told you additive rule is sorry, where's the additive rule? I can't find it. I guess here we have. This is the additive rule. And I told you here this is written in terms of probability. No? If we want, we can write in terms of number of elements. So we are going to use that rule to find that people who have both high level of cholesterol and high blood pressure. Okay. Okay. Give me a second. I will explain it. Okay. Let's say the number of people who have high blood pressure and high level of cholesterol, that means both of diseases, um, are X. You can take any symbol, right? Then there are 15 people who have high blood pressure, right? That 15 includes this X as well. There are 25 people who have cholesterol. That 25 might that 25 includes this X. X means number of people who have both diseases. Okay, X. Therefore, this region can be written as 25 minus X. This is 20, it's not 20, 15 minus X. Now tell me, what do you mean by this 25 minus X and 15 minus X? 25 minus X is what? 25 minus X is the people who have cholesterol only. They have only cholesterol. They do not have high blood pressure, right? They have cholesterol only. 15 minus X means the people who have high blood pressure only. They do not have any other disease. They have high blood pressure only. Therefore, if we want to find the value of X, right, we can write a small formula that is what? N A union B is equal to NA plus NB minus NA intersection B. NA union B is what? How can we write it? Actually, we can find the value of X in both, in two methods, right? In two ways. If one is we can use this formula. Without using this, we can actually easily find that value using this. We can write 15 minus X plus X plus 25 minus X plus 10 is going to be 40. The same rule. Okay. Okay. It's really easy to find. Therefore, we write 15 minus X plus X, this one, plus 25 minus X, which means number of people who have any of the disease. That should be 30. It is given in the problem. 15 minus X plus 25 minus X. Or you can write like this. 15 minus X plus X plus 25 minus X plus 10. There are 10 healthy people. That is equal to 40. All the people in that group. 40 people group, no. It's a group of 40 people. Therefore, you can write either first one or second one to find the value of X. Both are same. Right? If we subtract this 10 from both sides, finally we will get the same equation, 15 minus X plus X plus 25 minus X, that's equal to 30. Okay. Therefore, after solving this equation, you will get X as minus plus 0. 15 plus 25 is 40. 40 minus X is 30. 40 minus x is 30 means x is going to be 10, right? 40 minus x is 30, then x is going to be 10. Now we have found the value of 10. Okay. Give me a second, students. $25, $10. Then this 25 minus 10 becomes 15. 25 or 15. Here we had 15. Yes, 15 minus x. Sorry for that. Consider this. Blood pressure, cholesterol. Here we had 25 is 10. 15 minus 10 is 5. 25 minus 10 is 15. There are healthy 10 people. Now we have finished in a drawing Venn diagram. We are done, right? Now we have to answer these questions by looking at the Venn diagram. Okay. What is the first question? First question was to find number of people who have high blood pressure and high level of cholesterol. Here they are combining using this preposition and. How many people have high blood pressure and high level of cholesterol, which means we need to find number of people who have both diseases, not only high blood pressure or cholesterol, but we have to find the number of people who have both diseases, pressure, blood pressure and cholesterol. So how many people have both diseases? Only 10 people. Therefore, the answer for the first question is 10. 10 people have both diseases, high level of cholesterol and high blood pressure. They have both diseases, right? Okay, now go to the second question. If a person is selected at random, or if a person is selected randomly from this group, what is the probability that he or she has high blood pressure, has high level of cholesterol? Previously, the question was about number of people. But now, these two questions are about probabilities, not number, not a number. Okay? Therefore, please be very careful when you write answers for these questions. We need to find a probability for these two questions. If a person is selected randomly from this group, now we are taking one person, we are selecting one person from this entire group, not only from that 30 people who have any of the diseases, but we are selecting a one person from that group with 40 people, of 40 people. Understand? So if we select one person from that group, it asks the probability that he or she has high blood pressure. What is the probability of that event? I told you, we name that event as A, right? A. If we want to find the probability of A, how can we find it? Probability of A. That is equal to NA over NS. number of elements in the event A divided by number of elements in the sample space. How many elements are there in the event A? Is it 5 or 15? Is it 5 or 15? It asks, if a person is selected at random from this group, what is the probability that he or she has high blood pressure? It doesn't mention about the other disease. Anyway, that person must have high blood pressure. Sometimes that person might have other disease as well. We do not know about that. We need to find the probability that he or she has high blood pressure. අනිත් එක තිබුණත් නැත්නම් අපිට ප්‍රශ්න නැහැ. අපිට ඕනේ යාට high blood pressure තියෙනවද කියන එක විතරයි. So what is the probability that he or she has high blood pressure? Out of 40, do not write 30, right? Out of 40, we need to consider all the people. Why can't I write it? I don't know why. Out of 40, only 15 people have high blood pressure. Understand? High blood pressure have 15 people have high blood pressure. Not only high blood pressure, right? They have high blood pressure. Now this next question, he or she has high level of cholesterol. The probability that he or she has high level of cholesterol. Anyway, that person has to need to have cholesterol, high level of cholesterol. Sometimes that person may have high blood pressure also. We don't know about that. We need to find the probability that the selected person has high level of cholesterol. Therefore, the probability of event B or probability of this, according to this diagram, probability of C. So that can be written as 25 upon 40. Sometimes you might think the probability of B as 25 upon 30. No, it's not correct. Why? You need to consider all the people in that group. Because here it mentions if a person is selected randomly from this group. It doesn't mention randomly from the group who have diseases. It says if a person is selected randomly from this group. Therefore, that should be out of 40. 25 upon 40. Is that clear? Right. Now, next question. The probability that he or she has high blood pressure and high level of cholesterol. You are given a hint as well. There we need to find the people, not the people. Now, the probability that he or she has both diseases, high blood pressure and high level of cholesterol. That means it's related to the common region, the intersection part, event A and B. So how can we find that probability? Probability of A intersection B. N A intersection B divided by N S. That is equal to 10 over 40, because we have found A intersection B as 10. Here, this 10, okay? Right. So 10 upon 40 is the probability that he or she has high blood pressure and high level of cholesterol. Or we can ask the same question like this. The probability that she or he has both diseases. Okay, so you need to read the question very carefully before answering it. Okay, now see the next question. Probability that he or she has either high blood pressure or high level of cholesterol. That means if we select a one person from that group, okay, that person need to have either high blood pressure or high level of cholesterol or both. That term is not there, but or both phrase must be there, because if we select a one person from that group, he or she might have uh, either high blood pressure or high level of cholesterol or both. We do not know. So what is that probability? How can we find that probability? Definitely it should be out of 40. Out of 40, what is the number? Either high blood pressure or high level of cholesterol. Here we have, oh, no, either high blood pressure or high level of cholesterol means A union B. A union B is what? 5 plus 10 plus 15, 30. 5 plus 10 plus 15. A union B. 5 plus 10 plus 15. 25 plus 5, 30. Or you can find that value from the information given. Here it says, remaining 30 has either high blood pressure, a high level of cholesterol, or both. It mentions here. Therefore, without looking at the diagram, you can find that probability. 30 has either high blood pressure or high level of cholesterol or both. No? So we need to find, if we select a one person from the group, the probability that he or she has either high blood pressure or high level of cholesterol or both. So that is 30 upon 40. Understand? These are fractions. You can express these probabilities using decimals as well. If you want, you can simplify this as 3 upon 4, or you can write it as 0.75. Anyway, it's a number from 0 to 1. Or you can, if you want, you can write it as 3 by 4 is, if you want to write it as a percentage, 75 percentage. Right? So usually we use percentages, fractions, and decimals to represent probabilities. Understand? Is that clear, guys? I don't know whether you are listening to the lecture or you are doing anything else. Usually I don't like these online lectures because of that. What are you doing, guys? Are you listening or you are sleeping? I know this time is not good for lectures. After having lunch, you may be tired, or or maybe you want to sleep. But we have this lecture at 1 to 3, so we have to do it. Anyway, so far we discussed how to find this A union B, A intersection B, and probabilities of those events A, B, A union, A intersection, that. Now third, see the Roman 3, use part 2 to verify the addition law of probability. This. Now we need to verify the addition law of probability using the results we got from this Venn diagram. Okay, so here you are given the addition law. So we are going to verify this addition law using the results. Okay, can you do it at home, or do I need to do that here? Okay, I will explain to you how to start to verify an statement or verify an expression. Okay, so we need to verify this now. First we have to consider one side of that. expression. Let's take this right hand side, okay? If we consider the right hand side, that is PA plus PB minus PA intersection B. And PA was found earlier, that is 15 over 40 plus PB was found earlier, that is 25 over 40 minus A union B, probability of A, not union, A intersection B. Probability of A intersection B was found as 10 over 40, and that is equal to 15 plus 25 is 40, 40 minus 10 is 30, right? 30 over 40. And 30 over 40 was found earlier. That is what? Probability that he or she has either high blood pressure or high level of cholesterol or both. So that is going to be equal to probability of A union B, which was found earlier. That's the answer of part D. So that is equal to, that's going to be equal to left hand side of the given statement. So this is how we usually verify and state an expression. Okay, we need to consider one part first, one side. So using that side, we have to show the other side. Okay, so we are starting from the right hand side. Finally, we showed right hand side is equal to left hand side using the results we obtained in part 2. It's given, we have to use results of part 2. Understand? Okay, so that is the exercise number 2. There's another exercise. Okay, now I'm giving you this exercise number 3 as your first assignment. Okay, so far I didn't give you any of the assignment. No. This week you will get the first tutorial. That is different. Okay, so I will give you this exercise 3 as the first assignment. Okay, you have to submit the answer for this exercise within this week. Okay, I will upload this assignment to the LMS today itself. Okay, you can submit your answers for this exercise or this assignment to the same LMS course, right? Okay. Now consider the exercise number 4. An experiment consisted of flipping a coin and then flipping it a second time if a head occurs. If a tail occurs on the first flip, then a die is tossed once. To list the elements of the sample space, providing the most information, we may construct the tree diagram. Okay, now read the question very carefully and try to draw a tree diagram or Venn diagram or any of the diagram to list the possible outcomes. Can you draw? First, read the question carefully. We have only 10 participants, including me. What about others? Okay. 1, 2, 3, 4. There are 4 students who are joining the lecture using one laptop or one phone. Others. Okay. Anyway, read the question and try to draw a tree diagram or Venn diagram for this situation. An experiment consisting of flipping a coin and then flipping it a second time. If a head occurs. There's a if condition. First, he or she flip a coin, and then he or she flip that coin again if he or she gets head. Otherwise, if a tail occurs on the first flip, then a die is tossed. If he or she gets a tail for the first outcome or the outcome of the coin first experiment, then he or she he doesn't flip a coin, but he or she toss a die. Okay, so it's better to draw a tree diagram when we have such a situation. First, the person flips a coin. If he gets head first, okay, then he flip the same coin again. But if he gets tail, or if a tail occurs, then he doesn't flip the coin. Instead of that, he tossed a die. Now, how we are going to construct the tree diagram for this situation? I will show you the particular tree diagram for this case. Here I have drawn it. First, it says flipping a coin, right? And then flipping it a second time if a head occurs. Neither. මුලින්ම flip කරන්නේ coin එකක් head આવොත් ආයෙ ඒකම flip කරනවා. If he gets tail, instead of flipping the coin, he tossed a die. Right? Therefore, to understand the possible outcomes for this experiment, it's better to draw a tree diagram. Okay? Okay, this is how we draw a tree diagram for this situation. First, he or she flip a coin. So what are the possible outcomes? What are the possible outcomes? What are the possible outcomes? Tell me. What are the possible outcomes?
Head and tail.
Yes, head and tail. Very good. So first we flip a coin. Therefore, we can get either head or tail. There are only two possible outcomes. Let's say first we get head, right? For the first outcome of the coin. If we get head, then the person again flips the same coin, right? Then what are the possible outcomes for the second flipping? Again, we will get head or tail, right? Head or tail. I can't write on this slide. I don't know why. Give me a second. Okay. Can you see my screen? Right. Now let's say I think something is wrong with my pencil. I can't write. Sorry for the inconvenience. Yes or no? Can you see my screen?
Yes, madam.
Okay, thank you. Right. We were discussing about how to draw a tree diagram when we have this type of situation. Okay. In this experiment, the person flip a coin first. Okay. So if he gets head first, okay, if head occurs, then he flip the coin again. So if he flip the coin again, what would be the possible outcome? There are only two outcomes, either getting a head or tail, right? So let's say he gets a tail instead of head in the first outcome. Okay, if he gets head, then he flip the coin again. Let's say he gets tail first. So if he gets tail, right? If he get tail, then he is not flipping the coin. Instead of that, he toss a die or he roll a die. Okay. So if he roll a fair die, what would be the possible outcomes? There are 6 possible outcomes. It may be either 1, 2, 3, 4, 5, or 6. Understand? So the outcome of the first experiment is H comma T, H O T. Outcome of the second is what? H comma T or 1, 2, 3, 4, 5, or 6. So these are the outcomes that we might get from this experiment. Now we want to write the sample points or the elements of the sample space. This is just a tree diagram. This is not enough to list the possible outcomes. These are the possible outcomes of separate experiments. No? The outcomes of flipping a coin and outcomes of tossing the die. We want to list all possible outcomes of the experiment. Therefore, we need to consider their sample points. So the sample points or the sample elements of this sample space can be written as the first pair is what? HH. He or she can get HH or HT. If he get head first, then the second outcome may be either head or tail. If he get tail first, then the second outcome may be either 1, 2, 3, 4, 5, 6. So the sample elements should be T1, T2, T3, T4, T5, T6 if he gets tail first. Altogether, there are how many possible outcomes? How many possible outcomes? 8 possible outcomes. Understand? 8 possible outcomes. If we want to find their probabilities, how can we find those probabilities? Now, let's say we want to find probability of getting head or probability of getting T4. How can we find these probabilities? Tell me. Okay. It's not actually hard to find these probabilities, but it's not easy. Therefore, I told you if we have this type of situation, it's better to draw a tree diagram. So using a tree diagram, we can list all possible samples, points or possible outcomes for the experiment, and we can easily find corresponding probabilities, or we can easily assign probabilities for those events or those outcomes. Okay, that's why we draw the tree diagram for this situation. So what now my question is, what is the probability of getting head first? Now forget about this part. Okay, forget about this part. Now tell me, if we flip a coin, what is the probability of getting a head? That should be what? Tell me. What is that probability? Half, because it has only two sides now, head or tail. Therefore, getting a tail is again the probability half. Okay, right. Now move on to the next part, that is flipping a coin or tossing a die, right? So if he flip the coin again, the same coin again, he or she might get head or tail. Okay, therefore getting a head, the probability corresponding to that event is what? Again half. Because half probability head level. Therefore, the probability of getting tail is again half. Understand? Right. Now come to the next branch. In this branch, what is the probability of getting number 1 on the uppermost face in the die? What is the probability? It has 6 sides. Therefore, the probability of getting number 1 when he tosses a die is 1 over 6. He also 1 over 6. 1 over 6, 1 over 6, 1 over 6, again 1 over 6. Now we have found separate probabilities for each and every outcome of flipping a coin or tossing a die. Understand? Still we didn't calculate or didn't find the probabilities of sample points in the sample space. We just found or we just calculated the probabilities, associated probabilities, right? Understand? Now let's move on to the next part, that is how to find these probabilities for sample points. Now we want to find the probability of getting HH. What is that probability? Half times half. Half times half. That is 1 over 4. If you want to find the probability of HT, that is half times half. Again 1 by 4. Right? Now, what is the probability of getting T1? T1 or Tn1. Tn1. That is half times 1 over 6. Half times 1 over 6. Half times 1 over 6. Likewise, you can get all the probabilities for each and every outcome. Understand? So, now tell me, what is the probability of getting H comma H or H and H? What is this probability? That's going to be 1 over 4. Probability of getting T4. What is that probability? T4. The corresponding probability is what? Half times 1 over 6. That is 1 over 12. Is that clear? So if you want to find probability of getting T comma 6. T comma 6 means what? Probability of getting T and 6. Both must occur, right? Must occur. T and 6. Therefore, that probability is going to be half times 1 over 6, that is 1 over 12. So if we have found these probabilities, associated probabilities correctly, right, we would have got these probabilities like this. If you add these probabilities, right, half plus half, it's going to be 1 for one branch. Okay, half plus half is 1. If you add these 6 probabilities, that's going to be 1 over 6 plus 1 over 6 plus up to 1 over 6, 6 times. Therefore, that's going to be 1. Understand? If you consider this one, you can see that half plus half is 1. If you consider this, half plus half is 1. If you consider this circle, again 1 over 6 plus 1 over 6 up to 1 over 6, it gives 1. Understand? So at the end of getting all the probabilities of each and every sample points, okay, you can add up all the probabilities, and finally that probability should be 1. You can add those things. Here, half times half is 1 over 4. So 1 over 4 plus 1 over 4 plus 1 over 12, 1 over 12, 1 over 12, 1 over 12, again 1 over 12, 1 over 12. Then this gives 1 over 4 plus 1 over 4 plus 6 over 12. Here 1 over 4 plus 1 over 4 means what? 2 over 4 plus 6 over 12. 2 over 4 is half. 6 over 12 is again half. Half plus half is going to be 1. Total probability is always equal to 1. That's why I told you the probability of the sample space is always equal to 1. Here, if you consider the case flipping a coin, right? Flipping a coin, there the sample space is H, T, H, O, T. Therefore, the probabilities corresponding to those events, H and T, half and half. If you add those two probabilities, you should get 1. Here also 1, here also 1. Finally, if you add those corresponding probabilities for the sample points, that would be again 1. The total probability is always equal to 1. Understand? Right. So next week we will start from tree diagrams. Here I just taught you how to construct a tree diagram when we have this difficult situation to understand, right? Therefore, next week we will start with tree diagrams, and we will discuss some problems from tree diagrams. Okay. So